So remember how when we were doing derivatives that we could do numerical derivatives on the calculator by actually entering in the function and telling it that we were going to take the derivative with respect to x and give it the value of x, and it would come back and tell us the answer, and we wouldn't have to do all of the integration if all we needed to do was, or all of the derivative, if all we needed was the value of the derivative at that point. Okay, well that's what we're going to do with integration. So even though I'm going to show you how to do these by hand in this PowerPoint, primarily we're going to do the ones that we don't have to actually calculate the area by hand. We're going to calculate it using the calculator, but you need to remember one thing. This is the area between two curves. So just like it was when we did the area between the x-axis and a function, sometimes that area would be partially positive and partially negative, and your calculator would assume that anything below the x-axis was negative and anything above the x-axis was positive, and combine the positive and negative and lead you to a wrong answer if you weren't careful. So we had to always graph it to see when we had that happen so that we would know where the x-intercept was, and then we would do two separate intervals. One for the area from the first value up to the x-intercept, and then the second one from the x-intercept up through the last value. That could happen here too. So the first step always in finding the area between two curves is to graph the two curves. First of all, to see where they intersect and if they intersect more than once. But second of all, because you're going to need to see which curve is on top, because that's always going to be the one you subtract from. It's always going to be, just like it was before, it's going to be top minus bottom. Okay? So we need to always graph these. Now, one of the examples we're going to do in this is if an executive knows how the savings from a new manufacturing process decline over time and how the costs of that process will increase, how could she compute the net savings and when that will cease, and then what will her total savings be for this process? So that's going to be our fourth example. So there's a lot of important applications of integrals that require finding the area between two curves.
Ms. Glenn?
Yes.
Are you going to give us the formula for the producer and consumer surplus?
Yes, you will have all the formulas on the test, but I will tell you in advance, there is not a problem on the test, either the exam or the final. There is not a problem for consumers or buyers surplus.
Okay, so we
Okay.
won't need.
No, you won't need the formula, but I'll give you all the formulas that go with chapter 15 with the exam. So you won't need to know what
That
formula.
isn't the homework lab.
Yeah, it is in the homework. I want to give you a homework problem, primarily because that's an economics problem, and a lot of you are in economics or will take economics, and you need to understand what consumers and buyers surplus is, because that's an economics topic. But it isn't a topic that you absolutely have to know for this class. So even though I'll talk about it so that you kind of see the big picture, and you have a homework problem about it, you're not going to see that on the test. Okay, that will not be a problem on the test. Promise. I promise.
Pinky promise.
Pinky promise. Okay. So remember, the way this works in this picture, this is easier to understand than what was on the previous slide. If the area between f of x and the x-axis is that blue area, and the area between g of x and the x-axis is that pink area, and we're looking to find the area between f of x and g of x, not that total area, and if we take the total area of f of x minus the area under g of x and subtract, we would have the area that we're interested in. But it's absolutely key that you graph these first, because you need to know which function is the function that's the furthest from the x-axis, the one that's on top. as it were. So this is actually the way it's set up. And again, the fact that f of x is equal to or greater than g of x is important because of the order that the functions are going to be subtracted. So always graph. So here's our first example. This one isn't a difficult example because we've got the area between a linear function and a parabola. And when you graph those two functions, what you see is that the linear function, g of x, is actually the one that's on top. So we're going to integrate it first. And we're going to integrate it from -1 to 2. And then the area bounded by f of x, negative x squared plus 1, and that function is also going to be integrated from -1 to 2. And remember, we're going to integrate those separately because the area that we want, part of it actually does fall below the x-axis, so we have to be cautious about this. So this is how we do this. We're going to draw a sketch of the four regions, which I already showed you. One of the ways that you can find out where the x-intercepts is you can find it algebraically. So if you want to find out where one is greater than the other or where there might be intersections, then you would set them equal to each other and solve the resulting quadratic equation for 0. You can also find out that that equation has no real roots because when you graph it, you're going to see that there are no actual intersection points. So by looking at where is negative x squared plus 1 equal to 2x plus 4, well, they aren't equal. They don't ever cross. They don't have any intersection points. So you can verify that algebraically, or you can verify it with the graph. The graph shows you that they are not. And in order to help us in a little while, I'm going to go ahead clear some of this off, and we will go ahead and get a graph going of this set of functions. So my y1 function in this case is going to be the one that I already know is on top. So I'm going to put the linear function in y1. And then I'm going to put the quadratic function in y2. And since we're only talking about the area going from -1 to 2, we really don't need a window that's substantially further out than, say, about -3 or -4 up to +3 or +4. So you can take a clue on what you should set your domain to by looking at what your two limits of integration are. And then you can either do zoom fit, or the fact we've already got a graph, we could set the window, but I'm going to do zoom fit because normally that's the way we would do it. And then adjust the window from there to see what we think we ought to have. So there we see our two functions. And you realize then that if we're only going from -2, which is out here where the x-intercept is of this function, to +2, which is, let's see, right about there, then we realize we don't really need to see a window that goes that far down the x-axis. So we're going to go back to the window, we're going to adjust a little bit. We don't need to go down to -15. -5 will do just fine. So that we can see a little clearer picture of our function. So once again, the area we're looking at is the area from here to about here. Okay? Now, if we do that integration by hand, and it's not a difficult one to do because these are easy functions to integrate, then we're going to actually be doing the integral of g of x minus f of x, which is 2x plus 4 minus negative x squared plus 1. You can go ahead and combine those two functions algebraically. So 2x plus 4 plus x squared minus 1 gives us this, and if we rearrange that, we get x squared plus 2x plus 3. You can actually also leave them totally separate and do an integral of each one, but doing one integral is probably easier than doing two of them. So if you combine them, then we're going to do the integral of this trinomial. So 2x squared, add 1 to your power, that makes it 3, and then divide by that power, so that's x to the third over 3. And then with 2x, you add 1 to the power, making that 2x squared, and then you divide by 2, which means the 2 in front of the x is going to cancel out, and you wind up with just x squared. And then 3, the integral of any constant is always that constant times x. So the integral of 3 is 3x. And then we're going to evaluate at 2 and at negative 1, and we're going to come up with the answer, which is 15. And of course you can do that on your calculator, doing the arithmetic by hand. If you're plugging in x to the third, that's going to be, to start with, we're going to use 2. So 2 to the third power divided by 3 plus 2 squared plus 3 times 2, and there's our first integral. So that's a total of 12 2/3. And then from that, we're going to subtract, again in parentheses. You're using negative 1 now, so we're going to have negative 1 to the third. Don't forget your parentheses. Because remember, you always put negative numbers in parentheses when you apply power. Divided by 3 plus negative 1 squared plus 3 times negative 1. And then close that final parenthesis. Hit enter and it gives us the answer as a decimal, but if you ask it to change that answer to a fraction, I did something wrong. Let me see what I did wrong.
I'm not 15 in my answer.
Okay, let me check my parentheses and everything. 2 to the third divided by 3 plus 2 squared plus 3 times 2 minus negative 1 to the third divided by 3 plus negative 1 squared minus 3. That's what I did wrong. Let me go back all the way to the beginning. And that first one is a fraction, as I said, is 12 2/3, which is 38 thirds. And where I made a mistake, no, it is plus 3 times negative 1. Negative sign. That was supposed to be a subtraction sign. And it does give us 15. Okay? So the arithmetic's a little tedious, but nothing we can't handle. However, since we want to know the area between these two, And since I already have those two functions in, y1 and y2, what we can do is we go to the math key and right below numerical derivative is function integral, which is of course its inverse. And what we want to do is we want to use the function that's in y1. Now you can type the functions in, or you can do y1 minus y2. But I'm actually just going to type the function in. You just have to be careful to type it in correctly. So the first function is 2x plus 4. And we're going to subtract the function negative x squared plus 1. And then we're going to put a comma, and the integration is with respect to x, and you want to put in the limits of integration in the correct order, or you will get a negative answer where you should have gotten a positive one. And I'll show you what happens by doing it both ways. If you do 2 comma negative 1, you get negative 15. So they don't go top then bottom. It always goes, you're actually integrating from negative 1, the leftmost number, to positive 2, the rightmost number. So it always goes from the lower limit to the upper limit, even though when you do your subtraction, it's the other way around. So what you want to do is put your limits in. The first one is negative 1, the one at the bottom. And then your second one is of course, positive 2. And that way you'll get the right sign. Okay? Any questions? Now, if you were going to do that on the test, what do I want to see? I'm pretty sure that's what you want to know, right? What do I want to see? I either want to see what's on the PowerPoint screen, or I want to see, and regardless of either one, I want to see a sketch of that graph. Doesn't have to be perfect, doesn't have to be beautiful, but I need to see what the graph looks like. I want to see a picture of the area you're integrating. Make sure why you did it the way you did it. Then I would want to see you put in your calculator the correct integral. Write down what you put on your calculator. Now if you've got an 84, it doesn't look like that. If you've got an 84, it actually looks like an integral. Okay, it makes a little integral sign. You put in your bottom number, you put in your top number, then you fill in your functions, and then at the very end you tell it x. Okay? The 84 actually looks like the integral, the 83 doesn't. So here's our next example. Find the area between the curves y equals 1/2 and x equals, and y equals x cubed. So again, the first thing you're going to want to do is you're going to want to put in those two functions. So there's x to the 1/2. There's x to the 3rd. And if you don't know anything at all about the two curves, and you have no idea what to do, the first thing you might want to do is just simply look at it on a standard window. So I'm going to pretend I don't know this is actually what it looks like. I'm going to just go to the standard window and see if I see anything. And I do. And I can see that whatever's going on here about places they intersect, it's going on really close down toward the origin. So that tells me what I should do is that I should reduce my graph down to much smaller. a much, much smaller window. Now there's three different ways to do that, but the way that I usually do it is, the way I have the most control, is I go to my window key and I reduce this down to -1 to about 2 to start with. And the same thing on the Y direction. And then if this doesn't work, then I adjust again. So there goes the first curve. There's the second curve. And this does give me a pretty reasonable picture of what I've got. Okay? So I'm looking at the area between where they intersect here and where they intersect here. You can almost tell that they intersect there at the origin. You don't really need to, and it makes sense they intersect at the origin, because if you look at your two functions, if x is equal to 0, 0 squared is 0, and 0 to the third power is 0. So it's kind of obvious they intersect at 0, 0. Okay? But the other one is not necessarily obvious, and even though you can set them equal to each other and then factor and solve that way, it is far easier to go second trace, go down and choose intersect, click on both curves and let it guess where the intersection is, and it'll tell you exactly where the intersection is with no algebra required. So thus far, what I would want to see on this is I would want to see a sketch of the graph that looks like this. I would want to see where you've labeled the point 0, 0 as one of the intersection points, and the point 1, 1 is the other intersection point. So that I know why you're going to integrate from 0 to 1, because that's going to give you your limits of integration. Now the other thing that you want to pay attention to here is you need to know which function's on top. So hit your trace button and make sure you go to the top function and see which one that is. And it turns out to be the x to the 1/2 power is the one that's on top. So we're going to do x to the 1/2 minus x cubed when we do this integration. Okay? So this is the actual integral that we're going to set up. So I would see this with these 2 points labeled, and then you show me the integral set up, which means you're going to integrate from 0 to 1 of the function x to the 1/2 minus x to the third dx.
I'm sorry, why did you pick to integrate from 0 to 1 again? I'm sorry.
Because they intersect at 0, 0, and they intersect again at 1, 1.
So you just pick a point from each one?
No, you pick where the intersection points are.
Okay.
You have to find out where they intersect, and the x values where they intersect
Okay.
are your limits of integration. Okay? So the reason that we're setting this up this way is because they intersect at x equals 0 here, and they also intersect again at x equals 1, and all of the area between them is contained between 0 and 1. Because before that and after that, they diverge from each other. Okay? We're just trying to find where it's between. Now, this is the arithmetic way to do it. Okay? Oops. And you would set up the integral, and x to the 1/2 becomes x to the 3/2 divided by 3/2 minus x cubed's integral is x to the 4th divided by 4. And then they switch the 3/2 into a multiplier of 2/3. Plug in 0, plug in 1. Obviously, I hope if you plug in 0, you get 0, so you're not going to be subtracting anything. So this is actually all for plugging in 1. So this is going to be 2/3 times 1 minus 1/4 minus 0. Because when you plug in x equals 0, everything just becomes 0. And the answer is 15/2. If you do it on your calculator, you can go to your home screen and basically do function integral math And you can either type in the two functions, which I did last time, or since we've already stored them and you know how to find this, it's just as easy to type in vars over to y vars function y1 minus vars over to y vars function y2 with respect to x from x equals 0 to x equals 1. Close your parentheses. And it has to think about it for a minute. And it comes up with that. Now, if you ask it to do that as a fraction to start with, it says, no, that's too much trouble. Okay? I'm not doing that as a fraction. I don't want to do it as a fraction. It's too much trouble. But 5/12 is 0.4166666, so it's still the same answer. So I don't care if you tell me the answer is 5/12 or if you tell me the answer is 0.416 repeating. Either one is fine. It's the same answer. Okay? Once again, be sure you go from 0 to 1, not from 1 to 0, or it'll make your answer negative.
How did you get to the first part of like the F and
That's math and number 9.
math?
So you will accept decimal answers on the test?
Oh, yeah. Yeah, I'll accept decimal answers. And if we're actually going to do an application problem, I'll tell you how far around it before we use it. Okay? Because it may be that you'll need to round it. You wouldn't want to type in that whole thing. And since we had one, this is actually how it looks on your TI-84 calculator. And if you've got the TI-84 color, it'll actually let you differentiate between the colors of the two functions. So this slide might be one that you want to pay particular attention to because it walks you through all of the work to do it. Okay? Questions?
I can't figure out how to find the intersection. Give me a second, Tracy. Intersection.
Choose intersect, and then you should just have to hit enter 3 times as long as you can see the intersection for it. You have to be able to see it or it can't find it.
Okay.
Did it work?
Huh?
Okay. Okay, now the difference between two intervals can be used to find the area between the graphs of two functions, even if one of the graphs is below the x-axis. It really doesn't matter. Because what happens is basically f of x and g of x are families of functions, and there's no difference in this area being below the x-axis, which means both of these had negative x-intercepts, and both of them being above the x-axis, which means both of them had just simply positive or 0 intercepts. So you don't have to worry about an area that's split like this is, or where it's totally below the x-axis. The calculator will still calculate it. You will still be able to calculate it. The place where we do have to be careful, though, is where we have an area like this one. Okay? We do have to be careful when we've got a graph like this one. Because y equals x squared minus 2x is this parabola, and y equals x is this straight line. And notice that they intersect at 0, and they intersect at 3, and if all you wanted was the area between the two curves, that would be fine. Because you would just integrate from 0 to 3. But the problem here, it says find the area enclosed by those two functions on the interval from 0 to 4. So what we have to do here is we have to take this part of the integral and do it separately from this part. And it has to add those two together. And you have to do this regardless of whether you do the integration on the calculator or if you do it by hand. It doesn't matter. So the first thing you need to do is you need to find that intersection point. So we go to y equals and we enter x squared minus 2x. And then we enter y equals x. And since it only wants from the interval from 0 to 4, there's no point in going very far outside that interval. So we go to the window and go from -1 to about 5. So that we can see beyond -1 and beyond 4, but not too far because we really don't care what happens after that. And then again, I'm going to start out with zoom 0, which is zoom fit. And then I'll adjust the window to where we can actually see it better. So when it first draws it, it draws a really weird window. Okay? And if you look at the window, for whatever reason, it decided it needed to go from -1 all the way up to 125, which is not much help for us. So we'll go a little bit further down than -1, like maybe -10. Maybe, well, let's try 5, -5. And we sure don't need to see all the way up to 125. So maybe we'll only go to about 10. And check the graph again to see if this looks a little better. And
I think what you're saying is whether you put x cubed.
yeah, I did. I just realized that. No wonder it chose such a weird window. But there again, what you do is you use zoom 0 to get it on the window so that you can get an idea of where your enclosed area is. So the area that I'm looking for is this area right in here. Plus, from here to 4, I'm looking at this area right in here, this little triangle-shaped area. And I have to get those two areas separately. I can't do it all at one time. So what we first need to do is we need to verify where they cross. And again, that's easier to do without doing algebra. Let's just do it on the calculator. We've already got it in front of us. Second trace, choose number 5, intersect. And the only thing you have to be careful of, since it's kind of obvious they cross at 0, 0, you don't want it to find 0, 0 for you. You already know that. You want to trace close to the one that you want it to find to make sure it finds the one you want, since there's 2. And it says, okay, it intersects at the point 3, 3. That's the x value 3. So on the integral from 0 to 4, we're going to go first from 0 to 3 and get this piece of area. Then we're going to go from 3 to 4 and get this little remaining piece of area out here. Okay? So when you set your integral up, you would have to set it up that way. And you realize another thing too, this is why it's also important that you graph it and you break the integral up. On the interval from 0 to 3, which function's on top? The linear or the quadratic? The linear one is on top, so it's going to come first. So notice when we integrate from 0 to 3, we're going to say x minus the quadratic function. But then once we pass 3, which function's on top? The quadratic's on top. So it has to come first. So then we will go from 3 to 4 for the integral. We put the quadratic first and the linear is subtracted from it. Okay? So that's why it's important to graph it and find your intersection points, because you need to look at that graph. A good sketch of that graph is going to have to be part of your solution to these problems. Okay? Now, once we've got that set up, how you do the integration is up to you. You can do it algebraically and arithmetic, or you can still do it using function integral. So, remembering which is which, my quadratic is y1, my linear is y2. So I have to be careful which way I put them in unless I actually type in the functions. Go to math, choose number 9. Not there though. Choose math, number 9, and remember that it's going to be the linear one, which is y2, that comes first. Minus the quadratic one, which is in y1. And it's with respect to x. And the lower limit for this first half is going to go from 0 to 3. And it says that area is 4.5. And then you can switch them around and do y1 minus y2, and then change your limits from 3 to 4, and you get 1.833333. And sometimes it'll actually change that to a fraction. Let's see if it will. So that's going to be 11 over 6. So 4.5 minus 11 over 6. Oh, I'm sorry, plus, not minus. Plus 11 over 6. And since they have theirs as a fraction, we'll put ours as a fraction. It's 19 over 3. Okay? Okay.
Both my answers came out as negative.
Let me see what you put in. I think I know why, but I need to make sure.
So that's the bigger part. Here's the minus.
Okay.
And that's made equal for 3 to 4.
You've got your limits upside down. 0's on the bottom, 3's on top. So it goes low to high. Okay, that's all. Anytime you reverse your limits, it'll make your area negative. Okay? Now, it is possible to do this all in one fell swoop. You don't have to do 2 separate answers. What you can do, and this time I'll type the functions in so you can see you don't actually have to use the y1 if you don't want to. Function integral of, the first one is going to be x minus the quadratic function, x squared minus 2x. Close your parentheses. Remember, you do need that second set of parentheses because you're subtracting that whole second function. Then a comma, then the x, and remember your lower limit has to come first, so this is the part of the integral that goes from 0 to 3. Close those parentheses up and then go ahead and hit your addition button. And then go back to math and choose number 9, because we're doing another integral. This time we're going to take x squared minus 2x, and we're going to subtract x from it. And that's going to be with respect to x, and that's going to go from 3 to 4. And then again, close your parentheses again. So you can put that whole thing in, and you can get your answer as a fraction sometimes. Sometimes it gets hateful and says, no, I'm gonna give you decimal. And then sometimes it'll actually give you the fraction. So you can always throw in frac at the end of it if you really want your answer to be a fraction. And this time it actually does it. I think it just depends on how contrary the calculator feels and how ugly the numbers get. Okay? Now, if this was an applications problem, we might not want the fraction answer. We might prefer to have a decimal answer. If the result of the integral was maybe total cost, then we might need a decimal so we can make it into money. Okay? But again, the key is you've got to find the intersection point and you have to make it into two integrals. So your first integral goes from the beginning of the interval to the intersection point. Your second one goes from the intersection point to the end of the interval. Okay? This making sense to everybody? You like this better than the rest of it?
Yeah.
Yeah, I figured you would. At least we end up on something that makes us all happy. So here's example 4, the problem that we started out with. A company is considering a new manufacturing process in one of its plants. The new process provides substantial initial savings, but the savings are going to decline over time. And time is T in years, according to the rate of savings function, in other words, the marginal savings function of S prime of T is equal to 100 minus T squared. S prime of T is in thousands of dollars per year. Always pay attention to your units, that's very important. At the same time, the cost of operating the new process increases with time T in years, according to the rate of cost function in thousands of dollars per year. So this is your marginal cost function. And it's T squared plus 14 over 3 times T. So the first question is, how many years will a company realize savings? For how many years will they actually save some money? Okay? And then what will be the total net savings during that period? First thing we're going to do in order to answer the question is we're going to graph S prime of T and C prime of T. So we're going to go to Y equals, and C prime of T is T squared plus 14 over 3T. We're going to use X.
We put that 14 over 3T in the calculator. I always put my fractions in parentheses.
You should if you're using an 83, although your 84 may
I
have
got
a fraction.
84.
Does yours have a fraction? Will it make a fraction if you put it in parentheses anyway, just to be on the safe
And
side?
they put the variable on the outside.
Yeah. Some of the 83s actually have a fraction bar, some don't. Okay? So there's C prime of T. S prime of T is 100 minus X squared. Okay? Now to begin with, I don't know how long they're going to realize savings, and neither do you. So the best thing to do is realize that, first of all, time isn't going to go less than 0. You know, that's the initial time when they initiated the process. We have no idea how long they might save money. So we might choose to go to 10, we might choose to go to 50. I start small. I'll try and say, well, okay, maybe they'll save money for about 15 years. Let's see. I'm going to play like I don't know what this graph looks like. And then I'm going to go zoom 0 and let the calculator fit a window to that domain. So there's one of the functions, there goes the other ones. And I realize that this is where the savings are over with. Okay? That's where the savings are over with. So-
664.
That's at 664. I may not know that yet on my calculator, but it does show that on the picture here. So I realized too here, well, they're not gonna keep on saving any money after about 10 years. So I don't really need to look at that whole window. I can probably see better if I go back here to my window and just go from 0 to 10.
Your Y should be like what, like 0
Well, I can leave it where it is right now, or I can realize that, this is going way too high.
I think you're supposed to use.
So I go back to my window again and say, I don't really need to go all the way up to 295. Let's just go to about 150. And I don't really need to go down to a negative 125. Let's just go down to negative 25. And look at my graph again. So if you practice with this a little bit, the graphing window becomes easier to set up. But Zoom 0 gets you where you want to be. It gets you started. Okay?
Just a zoom fit, right?
It's just Zoom fit. Yeah, mine is 0. I think there's more on the 84 than there is on mine. So what we really need to know is we know that savings, that's your top function there, there's your savings function, is higher than your cost, which is your bottom function, until the intersection point. So in order to find the total amount of savings, we need to know what that intersection point is. So we go second, trace, choose number 5, and let it find the intersection point, and it says that it intersects at 6,64, which tells you basically at the end of the 6th year, both your cost and your savings is $64,000. Okay, they equal each other out. They wash each other out. So one reason we need the graph is to realize that it's S of t which is 100 minus x squared, is our top function. Therefore, it comes first in the integration. And then x squared plus 14 over 3x is our bottom function, so it's going to be subtracted from S of t. It's going to be savings minus cost.
How do we determine that top and bottom thing there, like your 100 minus x squared? What's the top of
You just hit the trace button and put your cursor on the top one to see which one it says that it is. Okay?
So we know that we're going to take the top function first.
The top function is going to come first when we write the integral. And the bottom function is going to come second, and that's the x squared plus 14 over 3x. Okay? Now the way they found the intersection point was they solved a quadratic equation. We've got a calculator. We're not going to solve the quadratic equation. If we can just draw a graph of it, we need the graph anyway. So 6 is the only meaningful solution, and that means your total savings are going to be the integral from 0 to 6 of your savings function minus your cost function. Or actually your marginal savings function minus your marginal cost function, since what we're trying to do is get back to the savings and the cost.
You want to go from 0 to 6?
You want to go from 0 to 6.
So that's all savings for 6 years?
They're actually going to have savings for 6 years. After that, savings is over, cost is going to increase, and the savings is going to taper off. So on our screen then, we want to go to function integral. And if you want to use y1 and y2, you can, but be sure that you do y2 minus y1, because y2 is your actual savings function. I'm just gonna type them in. So, my first function is 100 minus x squared. Anytime I have a multi-term function, I always put it in the expression in parentheses. Make sure that I'm doing it right. And then I'm going to subtract my rate of cost function, which is x squared, plus in parentheses 14 divided by 3 times x. So there's my function defined by both expressions. That's with respect to x, and I'm going to say from year 0 to year 6. And since this is money, I don't care if it's a fraction or not. So we're just going to go straight to a decimal. And in this case, it comes out to be an integer value. So what that means, remember that your savings and your cost is in thousands of dollars. That's going to be $372,000 that they save over a 6-year period. Okay? Any questions? Okay, I showed you another way to actually do this integration. This way is less intuitive than the other way. You can actually do the integration on your calculator and do it as a graph. What you have to do this is you have your two functions in there. But what you have to do once you've got them both in there is you have to turn them off. You actually want to see a graph. And the interesting thing is the graph doesn't look like the area of what you're actually finding. The picture looks different, but it's still the right answer. So then what you do is, at this point, you go to your Calc menu, and just like you can find the value of your derivative on your graph at any point that you want to, you can also find the value of an integral, and it'll show you the area that it's totaling up. Well, it should. Oh, it's not doing anything because I forgot to tell it to put the integral in there. So I'm doing y2 minus y1. So what I wanted to do is I wanted to show me the difference between y2 and y1 by integrating that function. So I go to the Calc menu. I choose the integral of function. It draws a graph of the difference between those two functions. And then it says, okay, what are your limits? Well, my lower limit is 0, and my upper limit is 6. And notice here that it actually intersects at 6. And it says, well, the difference between those two functions, the area under the curve that is the difference between those two functions is 372. Just be careful that if you look at this, that you don't think that that's actually a picture that's going to match that, because it doesn't. What it actually matches is this, the algebraic simplification of y1 subtracted from y2. But it'll actually shade on the graph for you. I like the numerical integration on the calculator home screen better because I need to draw the other graph. I don't necessarily need a graph of the actual difference. Okay? Now, keep in mind, the answer to a problem may not always be an integer. An example 4, solutions might be 6.7 and negative 7.3, and it might not be realistic to use a new process for 6.7 years. So what you would do if your answer doesn't come out to be an integer for the intersection point is you evaluate your integral from the beginning to 6, then you evaluate your integral from the beginning to 7 and see which one gives you the optimal answer. So if your intersection point does not come out to be an integer, go to the two nearest whole numbers, okay? And then you decide which one's the best. Now, this is the last problem that we're going to talk about. If you're in economics or you will be in economics, you will talk about this. So that you have an understanding of what the process is. Have you ever gone to the store to buy something and you're figuring on paying, let's say, $10 for it? That's how much you plan to spend, but you get there and you find out you've lucked out and there's a sale. And it actually only costs you $7 or $8. Okay? You feel pretty good about that because you saved the difference in what you were willing to spend and what you actually had to spend. That's called the consumer's surplus. You were willing to spend more than what the price of the item actually was. And according to supply and demand, the consumer's surplus is the difference between what the demand curve actually charges and what the equilibrium point is, which is where supply and demand are in equilibrium. So that area above that, where the demand curve, is going to be your consumer surplus. Now the same thing can actually happen with demand, but your consumer surplus is always going to be your demand equation, in other words, your demand price for a certain quantity, minus the equilibrium price. And you're always going to integrate it from 0, assuming that nobody wants any and you don't sell any, to whatever the demand quantity equilibrium point is, whatever Q is at the equilibrium point, the demand quantity.
That will not be on the test.
This is not going to be on the test, but as soon as you understand what the principle of it is.
It's in the homework.
Yeah. Now, you also can have a situation where sometimes the manufacturers are willing to supply a product at a price that's lower than the equilibrium price. Not talking about demand here, we're talking about supply. They're willing to supply it at a price lower than equilibrium. Of course, they're going to figure it out real quick and eventually charge the equilibrium price because that's where they're going to make more money. But in this case, what happens is the graph looks like this rather than like the first graph. Your producer's surplus is the area between the supply curve and the horizontal line through the equilibrium point. Which means if you have a problem like number 5 where you have a demand function and you have a supply function, you can find the consumer's and the producer's surplus, and it's not hard to do. It's actually very much like the one that we just did. Okay? What we want to do is we want to put the demand and the supply curves into our calculator. I'm not doing any of this by hand. So you go to your calculator and at y equals, and I'm going to clear all these out. At y equals, we're going to enter the demand curve, which is 344 minus 3 times E to the x over 2 power. And then we're gonna enter our supply function, which is E to the X over 2 power. Minus 1. And then, like we usually do, we know that we're not gonna go below 0, so we start at 0, but we have no idea where they're gonna intersect. So you can start out small or you can start out big. I'm gonna start out small and only go from 0 to 10. And let it fit the window. And if that's not far enough to see where they intersect, then I'll move X to be a little bit bigger. So there comes the demand curve. And it's going to be decreasing because demand decreases as price increases. There goes your supply curve. And it increases as the price increases because they want to make more money. And then what we need to know is where do they intersect, because that's the equilibrium point.
Mine is going the opposite way of yours. I don't really know why. What have I done?
That's it. That's okay. You were leaving your window on 0 to 10. You want to do zoom 0. Okay? That's all right. Okay, now we need to find the intersection point. And actually, I've already found it on you. You can see where it is, but I'll find it again. So choose number 5 and then just hit enter 3 times, because there's only one intersection point. And it says the intersection is at 8.9145 and the Y value is 85.25. Now what that means is that the equilibrium,
I'm not getting that done.
you're not? Check your functions.
X raised to the X divided by 2 minus 1.
Right.
Minus 3E X divided by 2.
Okay, what window are you on?
I think you put an X instead of an E in, or one of
The
these.
intersection point should be the same.
So your functions look like mine, but the intersection point doesn't.
It's ours, but it's, you got different calculations.
Let me look at your calculator. That's right. Oh, okay.
See, that's what I was asking about, because I was like, what? Oh my God, like, is it loving for like the situation? I don't want to be like everybody else. I want to be good at this other stuff. Like, I don't want to be general, like, I want to do something that will
I don't know. I'm not sure why without it. So I couldn't see the intersection.
Well, I was
So like that, really, really. That's exactly. And I was yeah, we're gonna do that. And then I was like, that's not it. Like, this is, it's not much. This is another $30,000. So I'm like,
Okay. Now, here's the thing you gotta understand about your intersection point. X is taking the place of Q. Q is quantity. Okay, Q is quantity. Our intersection point is not an even number. So actually the quantity is either going to be 8 or 9 realistically. So we're going to try to use that intersection point. The key is though is that 85.25 is the equilibrium price in dollars per ton. So that's $85.25 per ton. That's the line that we need to draw. So I'm going to go back here on y equals and put in 85.25. So that you understand here, what we need is this area up here. This is the consumer's surplus. So it's going to be the difference between the consumer's equation minus that 85.25. This is the producer's surplus down here. It's going to be 85.25 minus the producer's surplus, or minus the producer's equation. Now the reason I had you do it that way is because if you try to solve that logarithm or solve it algebraically, you have to use logarithms. Which is why I keep telling you, use your calculator to find intersection points. That way you don't need to know as much algebra. So our first integral for the consumer surplus is going to be the function minus the 85.25 going from 0 to 8.9145. And you can set that up on your calculator. Your consumer surplus turns out to be $1,795.13 total. When you evaluate that integral, that's what you get. Your producer surplus is much smaller than the consumer surplus because when you do your producer surplus, you take your 85.25, your equilibrium price, and subtract your producer's curve, your supply curve, and you integrate from 0 to 8.9145, and it turns out to be 598.38. So consumer surplus is a lot higher than your producer surplus. And the reason for that is because in this case your demand curve is more elastic than your supply curve. The supply curve, notice, is relatively flat. It doesn't really have very much room for wiggle, whereas your demand curve changes radically, so it's much more elastic. Now we could take both of those and calculate the elasticity of both those functions and realize that that's why. But rather than calculate it, I'm just telling you outright that it's because the demand equation is more elastic than the supply equation is. Producers have more constraints on what they're able to do within their price range of materials and labor and that kind of thing. The demand is elastic, probably because this is not an item that they have to have. So if it's cheap, they're going to buy it, and if it gets too expensive, they're not going to buy it. Okay? So you do have one homework problem like that. It isn't very much different from this one. And that's the last problem. It's the one you've been looking for all semester long. Okay? Hey.
On the review quiz, there's, on number 5, it's 15.6. It talks about Simpson's rule, and I looked up Simpson's rule, it's under 15.6 off now.
Okay, I must have not realized that we needed to take that one off. I'll just give everybody credit for that one.
Number 5.
Yeah, I'll just go in. Let me make a note.
Is it all the same numbers? Same questions and numbers?
Mhm.
Because I don't know if everybody has that same one for question five.
You know, it might not be.
It's not.
I'll have to go in and find it. But I can find it because it'll say it's out of section 15.6.
Okay.
But I'll just omit that question from the pool.
Okay. So I can submit it, but you'll.
Yeah, go ahead and submit it and we'll give you credit for it. Okay. I did not give you your practice problems out, correct? Or did I? Okay, since I forgot to bring them with me, I'm going to post them in Shovie, print them out, bring them out on paper with you on Thursday. I do have the video of me working through the last test. I haven't got it posted in YouTube yet, but it is posted in D2L for anybody that needs it right this minute. I was waiting for the link to upload last night and it never did upload before I went to bed. So I've got to go see if it uploaded the link and then I can post it to show you. It is on YouTube.
That's the video.
It's me working through the last test. The test over 12, 13, 14. Okay?
I thought we were getting part of our test to take home that.
Yeah, I'm gonna send it to you and show you. Unless you want to follow me and get a paper copy, I do have them, I just forgot to bring them.
Try with the number.